Now let's compute the following limit. The limit of ln x plus 1 over x as x goes to 0. What's this limit? Okay, so note that if we define the function f of x as ln of x plus 1 and we try to find the derivative at 0, by the way, the derivative is f prime of x is 1 over x plus 1, and this function is defined for x bigger than minus 1. So f prime of 0 is the limit as x goes to 0 of f of x plus 0 minus f of 0 over x minus 0, which is x. So here, when we plug the values, we get f of x plus 0 is just f of x. It's ln of x plus 1 minus f of 0. F of 0 is ln of 1, which is 0 over x. And x goes to 0. So here, just this limit is just the derivative of at 0 of the ln of x plus 1. And we know the derivative here is 1 over x. So when we plug 0, we get 1. Okay, this is one way to do it. Another way to do that is we can define a function. Let's call our function f of t. It's called ln t plus 1, t bigger than minus 1, and we're gonna use the mean value theorem, okay, to get the same result that we get here. The mean value theorem is very critical and very important, and one needs to learn it for calculus, for this result. Some of the these inequalities or these limits sometimes are very hard to find, but with the mean value theorem you can find them easily. So let's see. Let's check the conditions for the mean value theorem. So this function is defined. Let's choose the interval. Let's choose 0x as our interval with x positive, x real number. So in this case, our function f is defined on this interval, 0x. It's continuous. It's also differentiable on this interval, 0x. Therefore, there exists a constant c in this interval, 0x, such that f prime of c is f of x minus f of 0 over x minus 0, which is 0. So we know f of x is ln of x plus 1, and f of 0 is ln of 1, which is 1. So we have ln of x plus 1 over x. So next, what's f prime of c? We know f prime is 1 over x plus 1, so we have 1 over c plus 1 is ln of x plus 1 over x. Okay, next we need to bracket c plus 1. So we know that c is between 0 and x, because from here. Okay, so we add 1 to both sides, we get 1 plus c is between 1 and x plus 1. And we flip everything to get 1 over c plus 1 is between 1 over x plus 1 and 1. And what's 1 over c plus 1? It's this one. So we have ln of x plus 1 over x is between 1 and 1 over x plus 1. Okay. So now we get our result here. So now we take the limit. Okay. So the limit of 1 when x goes to 0 is always 1. Okay. The limit of 1 over x plus 1 when x goes to 0 is 1. So that means this limit of ln of x plus 1 over x is 1 as x goes to 0. So we use the squeeze theorem with these two functions. This is v is 1 and u is 1 over x plus 1. And we proved that the limit of ln of x plus 1 over x when x goes to 0 is 1. So this is using the mean value theorem. So a remark about this one is that you need to know how to choose your function, your domain, and check the conditions to apply to get the conclusion for the mean value theorem, to get this C, and after that you compute the derivatives and you try to locate where your C is, and you use algebra to find the f prime of C in terms of the x, and you get your conclusion. Anyways, we proved 2 ways. We can prove one more way, that this limit is 1. So we can graph the function x, okay, and also we can graph ln of x plus 1. So here, let me see, okay, here this is minus 1, okay, so let me graph it nicely. So this is ln of x plus 1, and you need to notice, oh, let me write this one in another bar, and you need to notice here is that this is y equals x. So when we are close to 0, the ln of x plus 1 and x, they look the same. This ratio is almost 1 because these two guys, they are not 0, but when you divide them, you get 1 because they are very close. So it's like 0.01 divided by 0.01, it's 1. And maybe smaller than this. So this is a graphic, like hand waving proof that this limit is 1.